propagation velocity equals 0.666 C. And then RL equals 150 ohm.
1 second. I should have brought some more markers. I got those that left now. Some of these markers have to work, I hope. Bad feeling. A lot of these. Well, listen. What the?
Here it is.
Remind me to throw all of them.
There we go.
Fine. All right. Back to this problem. What was RS on this one?
RS is 30 ohm.
30. And then the transmission line. Hold on. T equals 0. What was RL?
RL is 150 ohm.
Transmission line Z naught? 50.
50 ohms.
50 ohm, yeah, sorry.
Length?
Length is
What?
10 centimeters. And it says
And
plot out to 2 now.
Propagation speed? C?
2/3 C.
Yeah.
Okay, so for this problem, if you've done these problems, you realize we're gonna go get the reflection coefficients at the load and at the sourcing. We're gonna find out what V prime is, how much voltage the original pulse is that pops on that line. We're gonna find out the length of time that it takes to go down. After that, it's just a bounce diagram and reading from there. Okay, that's all it is. So, doesn't matter the order you do them in. Here, when I look at the reflection coefficient at the load, the impedance you're going into is 150, the impedance you're coming from is 50. That's a total of, it's going to be 100 ohms. Over the sum of the two is 200, so it's 1/2. Do y'all agree with that?
Yes.
If I'm wrong, let me know. When I'm looking back here, and I take a look at the reflection coefficient at the source, again, I'm going into 30 ohms here, right? And I'm coming from 50. Y'all with me? So that's going to be minus 20 over a total of 30 and 50 are 80, right? So that's minus, what, 1/4. Y'all agree with that? So this is minus 1/4. Now you've done a lot of these, so I'm not going to waste a lot of time with these explanations. Next, I need the time it takes to go down the line one time. And it doesn't matter how you denote this. So it's the length of the line, L, over the velocity on the line. Well, the length is 10 centimeters, 0.1 meters, right? And the velocity is 2/3 c. That's 2/3 the speed of light. The speed of light is 3 times 10 to the 8th meters per second. If you look at that, you're going to get 10 to the minus 1 over, and this is going to be simply 2 times 10 to the 8th, and that's 1/2 times 10 to the minus 9th. You all agree with me here? And so you can put it as half a nanosecond, or you can, doesn't matter, 0.5 nanoseconds is fine. Now we have that. The next thing we need is V prime. That's going to be the voltage that initially hops on that line at T equals 0. Do y'all follow me on this? How many are with me on this? If I'm going too fast. I hope I'm answering any question you can have about this, but this is a very, I mean, this kind of stuff is very obvious if you've done several problems, what I'm doing right now. So when I get V prime, what do I do, guys? I take Vs, right? And then I multiply it by Z naught over Rs plus Z naught. What is it for Rs? 10, right? And Z naught is 50, right? Over 50 plus RS is gonna be 80, right? So that's gonna be simply 5/8 times 10, or 50/8 volts, right? Y'all agree with that, class?
Yes.
All right, now for the bounce diagram, I'll do it here. So, all right, from here to here is TD, from here to here is 2 TD. This is 2 TD, so this would be 4 TD. And here is going to be the actual value of V prime. Here it's V prime times reflection coefficient of the load. Here it's V prime, reflection coefficient of the load, reflection coefficient of the source. And here it's going to be V prime, reflection coefficient of the load squared, reflection coefficient at the source, and so forth. You all with me? So now, where do they want the value of the voltage versus time? It's different at the load than it is halfway down the line or any other point. Y'all agree with me? Let's just get this. Go ahead. Where would you
We
like
wanted
it?
it the source, the load, and halfway down transmission line.
All right, at the source, this is the source right here. So if we look at this, you can see right here, just, I'll graph it, but y'all with me. At t equals 0 is when the switch closes, it hops on at V prime, right? Nothing changes until I hit this point, right? Now it's important to see this. There's a superposition of an incoming and an outgoing pulse at the same time. Y'all see that, everyone? So now it would change by adding V prime times gamma L plus gamma L gamma S. Y'all with me? Right here. You'd have to add it at that point. Then nothing happens again for 2 more TD, and at 4 TD, then you would have to add this one, and I didn't show this, but coming out here would be V prime times gamma L squared, gamma S squared. Y'all with me? You'd have to add these two. So we'll graph that right here, right? And I'll need your help maybe for a few values. So, V prime, what's that numerically, 50?
6.25.
Okay, 6.25 volts. So we take a look at voltage at the source versus time. Here's 0, it starts at 6.25. Here's 1 TD, 2 TD here. And then at that point, now I've got to add, well, just take gamma L plus gamma L gamma S. So gamma load is 1/2 plus 1/2 times minus 1/4 is minus 1/8. 1/2 minus 1/8 is 3/8, right? So it'd be 3/8 times V prime you'd add on here. And that's a positive, so it's going to be there, and then it's going to go up. And this value is going to be 3/8 V prime added on to 6.25. Can you give me that value? I'm curious. Anyone?
8.6.
I think it's 8.6.
8.6. All right, it stays there. Right? And here's where there's going to be a very slight change. Now, so it's going to stay at that value until I hit 4 TD, correct, class? Everybody with me? Now I have to add, and here's where it gets small. I have V prime, and the coefficient of that is going to be gamma L squared, where that's going to be 1/4, right? Times gamma S, which is minus 1/4. So it's minus 1/16 here, times V prime. And here it's going to be what? 1/4, and that's going to be 1/16, correct? 1/4 squared is 1/16, and so what is that? My gosh, 1/48. It's small. So if you add that, that's positive with this minus. So it's actually going to be a minus change. It's going to go down. Y'all agree with that, class? How much does it go down by? From 8.6 to something very, not much different. Like 8 point, what is it?
Yeah, it's 7.9.
Anybody get that? Now it's just running the numbers. Once you see what's going on. What do you got, folks? Anyone? Guys. What you get? Just take 8.6 and let's see, 1/4 minus 1/16 plus 1/48. So it's 3/48, 3/48 times V prime, whatever that is. And then, I don't know. It's actually, yeah, it's gonna be a negative change. What did you get?
Yeah, 8.2.
All right, I'll buy that. 8.2, and then it's just flat out. Are you with me, class? I'm not even gonna get the next bounce, because by that time you can't even see the difference. Follow me, everyone? So it's gonna asymptotically approach a stable, constant value. Now, at the load, what happens, do you wanna do the load next or the middle? The load is just like what we did there.
Yeah.
All right, there's gonna be a constant, 2 time constants between each change, right? You wanna do midway?
Just do midway.
So now, below here, we'll do it midway. By the way, when's our next home game? Anybody? Basketball.
It's away.
Huh?
You said the next home game. I'm not sure.
Oh, sorry. No, sorry. Not yet.
When do we play next? Maybe that's.
Play this weekend.
What?
We play this weekend.
Against,
Georgia.
7? Or is it an afternoon game?
It's a noon game.
It's at Georgia though. It's like not, it's not an Auburn, it's an away game.
Yeah, I know, but what time
It's
about?
at noon.
Noon? That's okay. All right, for this, what do we do, guys? I didn't show you this, but this would be L over 2. You go right down the center, correct, guys? Nothing happens until we get TD over 2, and that's the first transition here. And it just goes up to from 0, and this is going to be B prime, right? It stays there for how long?
2 NIS? No.
Well, think about this now.
Oh, it's
That's a full.
0.25.
So we're going to add on. It's going to be what? 1 or 3, 1.5 TD, right?
Oh, okay.
Right.
Okay, got it.
Follow me on
Yeah,
that,
yeah.
guys. We're adding. It's going to be from here to here is a half. From here to here is a half. It's a full TD. We're going to add on to the last time. So we go to 3 halves, which I didn't show, but would be right here. And now the only thing I'm going to do is what? I'm going to add 1/2 times V prime onto that. So it's really going to be 3 halves V prime, isn't it? Right there. And so this is going to go up to 3 halves V prime. It's going to stay there until I get 5 halves TD. And then what? This side I add on, right? And that's going to be gamma L, gamma S. So minus 1/4 times 1/2 is minus 1/8. So it's going to go down a little. I can give you the exact values, but I think you all follow me on this. And it's just going to continue, isn't it? And then the next change is there. Can you all follow me on that bounce diagram? Now, it is important to get the right values, but take your time. Make sure you get the reflection coefficient right and V prime right. I mean, the reflection coefficients at load and source, and do the math right. You don't have to fly through these. You with me? I know it's a little tedious, it gets boring too, but that's what you need to do. Yes?
So at each point on the line, they'll ask you type the approach value.
I'm sorry, what?
At each point on the line, it will ask you type the approach value.
Right, right. What
How do
happened?
you determine that?
Why don't we just ask the whole class this? If time went on forever, right, just let the thing bounce down so there's no change. What's the voltage at the load gonna be? Maybe a better question is, does the transmission line have any effect at all? None at all. It's like connecting that load right here. Y'all follow me? So the load anywhere on the the voltage anywhere on the transmission line is the same as T goes to infinity. Y'all hear me on that, guys? That's really important. They look like two pieces of copper that you just used to solder things, right? There's nothing that bounces after that. Everything goes to a constant. So if you're on the line anywhere, it will have the same voltage. What would that voltage be for this problem, by the way? As T goes to infinity, V on the line as T goes to infinity is going to be what? It looks like the 150 is right here, so it would be this voltage, 10, right? Over 150 plus 180. Correct, class? Y'all follow me? That's simple voltage. I'm going to say this right here. Guys, you got it? All right. And that's a good question, because I do ask that kind of a question on exams, especially that, and people that are just, I hate to say it, it's people that cram and just, you know, they're going to do it one night before the exam or before the quiz, then they get panicky and they don't see it. I promise they don't. And I see that on the finals. It really bothers me. I'll see so many really high grades, then all these, the bottom drops out. And I think it's cramming. That's my own opinion. All right. Anything else before I get on with my lecture? I thought I did chapter 3 questions, but that's okay. All right. So today, what I'd like to do is I want to go through, and this is real important, the coordinate systems. We talked about the basic physics. And what I've found when I teach this class is a lot of people understand the basic concept, the physical concept of electric field and of force, electrical force, but they have a hard time with the coordinate systems and unit vectors and differential surface and differential volume. So today I'm going to try to focus a little bit on the differential stuff that has to do with volume, length, and surface. Believe me, don't discount this. Don't get bored, because this is important. So, the coordinate system I'm most familiar with is Cartesian. Cartesian is x, y, and z. So when we have an ordered set of points, it's x, y, and z values of those points. Are you with me? You're familiar with this, right? The coordinate system itself, x would be here, y is here, z is here, and there's an origin. That's it. Now, when we take a look at a differential length, the differential just means an ever so small length in this coordinate system. Then there will be unit vectors associated with this. There will be a unit vector ax, a unit vector ay, and a unit vector az. And they're just in the coordinate axis directions. They have a magnitude of 1. Y'all with me, class? You've seen unit vectors, right? When we talk about differential length, that's going to be dx ax plus dy ay plus dz az. There's no mystery here. That's it. It's a differential length. Now when we take a look at a differential surface, what we have to do is first, really, to talk about that, we have to take a look at a differential unit of volume, dV. That's dx, dy, dz, and that's just a little differential cube. I'll draw it right here. It's just a cube. Here it's going to have dy, dx, and dz as the differential links on it. Are you with me? Now, a cube has 6 sides, right? So when we tell you, say differential surface, it's not just one, it's 6 possible. So if we're talking about this differential surface, now draw this and just focus right here once you get this. I want to make sure I get this point across, then it won't be trouble. This one point. A differential surface has a differential scalar area. So if I'm looking at the differential surface associated with this side, it would be that differential area, which would be dx dz. So I'm just saying, if I want this differential surface right here, it would be dx dz. Y'all follow me? It's just height that way. It's width times height in this case, right? And a differential surface has a direction. Now, when we talk about a differential surface, usually, but it depends on the actual problem statement, it is outward from the differential cube, like that. So it would be, in this case, it would be dy, or ay, pardon me, ay. Are you with me on that? How many see this right? All right, let me ask the class a question. Think about this. If I wanted the differential surface associated with this top right here, what would it be? Let's say ds for the top. Differential surface is a vector. It has a magnitude and a direction. What would the differential surface be? Just take a look. No wrong answers. It's really dx dy, right? And what direction is it? You're right.
AZ.
All right. Right. Hold that thought. Now don't say anything yet. Now what's the differential surface of the bottom that you can't even see, but down here? Now what is that going to be?
Same as the top.
Same magnitude, right? Only minus AZ. Y'all see that? So it's same as the top would be dx dy, only it would be minus AZ. And that's really it. In a nutshell, how you get differential surface. You got differential length, differential volume, differential surface. That's it for Cartesian. It gets a little more complicated with cylindrical. You've had cylindrical coordinates, but you're not immersed in them. So let me just show you cylindrical coordinates. And you can just listen. Well, for cylindrical coordinates, you use the z-axis, and then what we do, this is x and y, that's the xy plane. We don't use that. We actually have something, a vector in the xy plane, and we call it rho, Greek letter rho. Rho itself is equal to the square root of x squared plus y squared. So it is really a vector that is the total length of the x and y excursion in the plane. Y'all follow me on that? Now, there's also an angle here, and that angle is phi, and it's always measured from the x-axis, looking down the z-axis. You look down the z-axis, take the x-axis, and then see what the angle is between the x-axis and the rho vector. So it's in the xy plane. Y'all see that, class? And so it's got an angle phi too. And the way we ordered these points, by the way, is rho, phi, and then the last one is the same thing as Cartesian, it's just z. Now here's where it gets a little tricky, and I want to make sure I say this. When you take a look at this, right here, you're going to see a unit vector. The unit vector, and this is not done in Dr. Winkler's book clearly, I don't think. This would be a rho. That's a unit vector that's in the direction of the rho vector, but it's radially outward. Y'all see that, class? Now, there is a vector AZ as before in this direction, the unit vector. Now I have to make a comment to make sure it's clear. Can you see that as this angle phi changes, the actual direction of a rho changes? What I mean by that, suppose this is going to be a rho for a given rho, right? Well, as phi changes, can you see how it's actually changing? Over here, these vector directions never change. If you look at the direction of the vector, the unit vector, it's always the same. Here, the unit vector's direction is dependent on the value of phi. And this is a little troubling, but we'll get over it. I'll explain why. All right. Now, AZ is still up. There's also one other vector, and that's A phi. A phi is a unit vector A phi. A phi is perpendicular to A rho, and it's in this direction. Now, I gotta be really clear about this. What I wanna do is get rid of the z-axis so I can just focus on what's really going on. Look straight down the z-axis and you're gonna have this. You have some x and some y. All right, we're looking right down the z-axis. Can you all imagine that, people? Now, I'm gonna come out some distance, rho, and I can say this is the angle phi, right? Now, A rho is this way, right? And A phi measured from the x-axis to the actual, to rho, that's phi, and A phi will be in this direction. Now, you see how those things are oriented right there, correct, class? Now, what I'm going to do is increase the angle phi. Now, watch. Just do this with me in your head. What happens over here? I'm going to have the same length rho here and here. This will be rho. But now my A rho is in this direction, and my A phi is in this direction. Now, the important thing to appreciate about this is that at the point that we're talking about, where we have coordinate rho, phi, and z, A rho, A phi, and AZ are orthogonal. They're orthogonal here. They're at 90 degrees to everything. But the actual vector direction, A rho, is a function of the angle phi. And here's something else. These things have a relationship to the XYZ coordinates. Rho is just equal to the square root of x squared plus y squared. That should make sense to everybody. Phi is really, if you look at this, phi is really going to be, well, this shows it better. Since this is the x coordinate right here, whatever it might be, and this would be the y coordinate, then you can see opposite over adjacent would be the tangent of phi. Can you all see that? So the inverse tan for phi itself can be given as tan to the -1 of y over x. And remember, any point, we're talking about points here, any point that has an XYZ point, it has an associated rho, phi, or rho, phi, and z point. The z doesn't change. Are you with me, class? How many understand that? How many have had cylindrical coordinates, some version of it, right? You should have, everybody in your math classes should have been exposed to this at some level. It's just, I don't know how deep they go into the discussion, if they go through differential links and all that. All right, now, so that's the coordinate system. Now, when we take a look at a differential link, this is important. A differential length is sort of, if I'm at the tip of this vector and I start wobbling it, if I get a d phi, a dz, and then a d rho, what would the differential vector look like? So it looks like this for cylindrical, and I'm gonna erase that and put it right there. I'll leave those there. But the differential link, it looks like simply d rho, a rho, which is nice. But now the next one's a little different. Then I add on rho d phi, a phi, plus dz, az. And this is the one that troubles people. Well, how did you get that? Let me show you exactly how I get that. If you go ahead and write that down, I'll show you. So if you have this rho, and we hold it constant, and this is phi. Y'all with me? Now, if you wobble that a little, and you get some d phi right here, the tip of this actually moves in this direction. Can you all see this? I'm holding rho constant, I'm adding a slight amount of angle. Can you imagine that? Well, then, if you look at this, this rho vector would be the same, but I would move across the tip. And the tips, the amount of distance that that tip moved would be rho d phi in the a phi direction. Think of a windshield wiper for a second. Go to the end of your windshield wiper. Say the windshield wiper has a length rho. Now if you move through any arc length in radians, right? How far did that tip of that windshield wiper move? It would be the length rho times the actual angular difference. Do y'all remember that, class? If you're talking about an arc length on a circle, if you have a constant radius, rho here, and you ask how far is this, well, what you're really asking is what this is, and this length here would be rho and times just theta. And if it's a differential, it's rho d theta. Does that make sense? You with me on that? I mean, if you want to take it to the logical extreme, well, what if you go all the way around the circle? Well, that's 2 pi radians, right? 2 pi times rho is the circumference of a circle. Agreed? Okay, so that's the differential unit length. Now, differential volume is next. Well, differential volume is really just the differentials associated that are in front of those unit vectors. You just multiply them together because it's orthogonal. So it's simply equal to d rho, let me do it this way, d rho times rho d phi times dz. That's the differential unit of volume, and it is a cube, even though it's a cube. You might say the sides are not always oriented in the same direction. They do move depending on the value of phi. And what about the differential unit of surface? Now this is not my strong suit. Now I have to draw my differential unit of volume in cylindrical coordinates. So bear with me, I'll do my best. It's in your book, but I prefer to give you something on the board. So if we take the x, y, and z coordinates here, and now I'm going to come out a differential amount, and you're going to see a cube appear here. Let me try this one. This is in your book. This length would be rho d phi. This would be dz. And the radial difference would simply be d rho. I hope you can appreciate that's supposed to be a cube. If you look in your book, if anybody can give me a page number where it is, I'd appreciate it. You'll have a differential unit of volume for cylindrical on some page. I just don't know what it is off the top of my head. No? It's in there somewhere. I'm going to send you a PDF that's got all the stuff I'm doing on the
121.
121, thank you. But that, so if you look at this, and this is not drawn to scale, not drawn large enough, but just hear me now. So if I wanted the differential surface, hear me now, differential surface out here, can you all see that in the back? That's rho d phi this way, dz that way. You would go ahead and take rho d phi that way, right? If I wanted the differential surface, and this would be on this outer one right there, it would be equal to this differential, which would be rho d phi, times the height, the differential height, dz, and it has to be in a direction perpendicular to these differentials, or it has to be a rho. Make sense there? A rho. Now, if, I'm not going to do this, but if I got to the back side and I wanted the differential on the inner surface, same magnitude, only minus a rho. You all follow me on that, class? Now, you try this once. I know it's an ugly, poor try, but just work with it. What if I wanted the differential surface on the top? Well, what would the actual scalar value be? What is it going radially? It is d rho, right? And what is it, the outer edge? Rho d phi. So it would be d rho times rho d phi. And what direction? Az. What if it was the bottom? Same exact, only minus az. Correct, class? Now, last one. What about this surface right here? Just think about it. Differential in the radial direction is d rho. In the vertical? All right, now what direction? Minus a phi. Yes, it's minus a phi. Very good. The other one would be positive a phi. Okay? You got to keep that in mind. I'm going to just tell you with spherical coordinates, same basic stuff, a little more complicated. What page do spherical coordinates start in your book? All right, page 128. Well, with spherical coordinates, as you might guess, they're based on a spherical shell, concentric spherical shell. So you're going to have some distance r, and that's the radial distance from the origin. And r is equal to the square root of r squared plus y squared plus z squared. It's just the radial distance from the origin to that point, x, y, z. Now, the next thing you have is an angle phi, or theta. So theta is measured from the z-axis to the r vector. All right? Theta can have a value from 0 to pi. With me on that? When it's straight down the south pole. 0 would be the north pole. So theta here, if we look at this, well, it's right there. And you can get this a couple ways. If you wanted theta, and if this was, since this is z, this would be z. So it would be, you could do it as opposite. Let's see here, what's the easiest way? You could get it with a tan function, and you could say, z over r was cosine theta, or theta is cosine minus 1 of z over r, but there are a lot of ways to get it. I'll just put this down as a possibility, because r is given up above. Now there's something else, and this is important, you see this. If I take the projection of r in the xy plane, it becomes rho. You all with me on this? This is important. And when we talk about phi in Cartesian is phi in cylindrical is the same as phi in spherical. Got me on that? They're the same. So if the points are rendered in x, y, and z, this right here is just the inverse tan of y over x. It's tan minus 1 of y over x for the coordinate points. So there's phi, and that's equal to tan minus 1 of y over x if you're talking about Cartesian coordinates. Now, if I go ahead and do the differential length and volume, I'll put those up for you, but it's the same process because we've got a quiz right now, and I just want to tell you one thing. The big thing about these is challenge yourself, do the homework problems I give you over the weekend, and on Monday, if you have questions, uncertainties, come and ask me, because this is what we use to describe everything we do in electrostatics and magnetostatics. You have to have these coordinate systems done. So now, give